Hello, this is my brand new ALU that I have been making, or Arithmetic Logic Unit. Usually found in computers, it's normally connected straight to the CPU. Sorry if the frame rate's just a little bit low, my computer isn't all the best. So, in case you're wondering what this little thing is, it's just something to remind me what the order of functions are. In this case, when everything is set to 0, it's an OR gate. When the first bit is on, NOR, etc., etc. But what does an ALU actually do, and what does this have to do with this? Well, an ALU, as the name implies, performs arithmetic, or performs certain operations on a number. So, let's see what functions we have here. This actually doesn't do anything, it's just a loop around and back, just so that the CPU, when I eventually add it, has some sort of idea how long it's taking. If I go over here, there it is, on, off. I know the quality is probably not too good. Non-calc ALU, I can actually remove that now. So, long story short, there are 3 main parts to this. Well, technically 4 if you count the flags. This is the number input panel. This is where you add 2 different 8-bit numbers. Let's say 5 and I don't know what number's that, 10. 5 and 10. So, we've just inputted 5 and 10. So what's it currently doing? Well, because this panel here, the function selector, has all bits set to 0. It's currently ORing them together. And we can see that in this output, it's ORed those 4 bits. Right? So, kind of complicated, but you can get the hang of it in a sense. So, that's nice and all, but what if we wanted to NOR them? Well, it's the first bit on and the rest off. So in this case, turn that on, and they are now NORed together, or not OR. I will just set these so that you can kind of see what's going on here. So, 2 off, 1 on, 2 on. And to NOR them together, essentially, if there are any switches on this bit, it turns off, otherwise it's on. I won't go through all the gates, you can probably look them up. For example, the XOR is this. Turn that on, turn that off. Now, in an XOR, it only turns on if only one of its inputs are on. So it should be off, on, off, 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 off. And what do we see here? Off, on, off, 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 off. I think that was 8 offs. Anyway, long story short, this, you just select what function and you put your numbers in. That's really quite handy. But you're probably wondering, that's good and all, but why not just use the functions? Well, it's because this would normally connect to a CPU, and the CPU would go, hey, I need to add the number 6 and 7, or XOR them, and it will give out its result. Now, I've got all the different gates, OR, NOR, AND, NAND, XOR, XNOR. The 4 implies gates, which I've only just recently come across. Add, subtract, and of course not. Now, not doesn't quite function properly, being that a NOT gate only has 1 input naturally, and there are 2 numbers, so what do we do there? Well, my only solution was to completely ignore this top row for the NOT gate, and just have the bottom row. So, let's add, so we will set it to add 2 and 4. So, the function has been selected to add. What numbers should we add? Let's add the same ones. So, 5 and 10. Yeah, 2 and 8. 5 plus 10 should be 15, or in binary, 1, 1, 1, 1, 0, 0, 0, 0. And there we go. The number 15. And we can subtract as well. So, if I just hit the switch, it's now in subtract. And if we have a look now... Ah, yes. You're probably wondering, well, what's happened here? Because of the way that it functions, I've accidentally selected 5 minus 10, not 10 minus 5. And because of that, the ALU can't really handle negative numbers. So it kind of gives this weird result that no one can understand. And then the ALU flag for the negative result while subtracting comes up, essentially saying, hey, you've done this backwards, there's an error. There are two ALU flags. One is negative result, and one is overflow while adding. Eventually, I will be adding compare functions. Is function A larger than B, smaller than or equal to? But I haven't implemented them yet. And as you can probably imagine, if we were to just flip these around... Huh, that was actually easier than I thought. So now we've got 1, 4, that's the number 5, 2, 8, that's the number 10. 10 minus 5 should be 5, or 1, 0, 0, 1. Oh, right, yep, 1 and 4, 5. So it subtracts correctly. But what happens if we add a really, really big number, one that it can't handle? Let's say 128 plus 128. Now, normally, 128 plus 128, that's 256. But in 8-bit numbers, you can't really show that. So, at the moment it's currently in subtract. 128 take 128 is, of course, 0. Showing no red flags there, everything's fine. But if we add it, again, we should show, or we should see, that there is some form of error. Just here. Overflow while adding. Essentially, 128 plus 128 is 256, but you can only add up to 255 in 8-bit numbers. To get 256, you need another bit. It would have to be 9-bit, which this ALU is not. So, instead, it just throws up a flag saying, hey, there's an error here, number's too big. Those two I've set over here to only activate when the add or subtract lines are, of course, functional. So at the moment I've got add enabled, and essentially this is the negative result ALU, and this is the addition overflow flag. These, no matter what you do, these will always output their answers, which naturally you don't want. You only want it to throw an error if these results, or if these flags show an error, and if you actually have this selected. I don't want there to be a negative result error if I'm trying to XOR some pieces together. It doesn't make sense. So what I've done is, in this very jumbled mess, I have used an AND gate. So essentially, it only turns the lamp all the way over there on, signaling a problem, if both the flag and its respective function is called. So, if this comes up with, hey, there's a negative result error, it will turn on this line naturally. But if I'm trying to say AND two values together and I don't care about negative results, then because this line is currently turned off, the output will be off, no matter what. So I've essentially done that. I don't really need to do that for all the others, and yeah. In case you're wondering how I've done, these are, well, these took me a while. They are 2 wide adders and subtractors. Essentially, this is the subtractor, this is the adder. The only difference is the inputs have been inverted on the subtractor and the output has been inverted. However, the inputs and outputs for the adder have not. That's the only difference between them. I could have added an XOR at the start and the end, but honestly I can't be bothered. So, just had to check my mic there. Essentially, that's kind of how this all functions. Now, this seems pretty okay. It actually functions, but let's take a look from above, because this actually looks really cool. Already you can see patterns appearing like that. And if you have a look, there are boxes like this one here, formed by essentially each adder and subtractor. Those things poking out the top are the adders and subtractors, because the carryout naturally has to go to the next bit. They were a real pain in the butt to get, but hey, it works. And of course, these triangles. Essentially, while underneath is fairly simple, it just takes the input of those switches to their respective areas. Unfortunately, it's not that simple for the option selector. So, if I set it back to, say, OR, essentially all this does is turns your binary number into its respective pieces. If I add 1, then that turns on. If I go to 2, etc., etc. So, what does this actually do? Well, the general idea is that this comes along and turns on the first bit, naturally. But the output comes all the way out here, all the way to the second bit, because each bit is naturally calculated separately. And then comes all the way over to the third bit, and so forth and so forth. Essentially, that's what these triangles are. Each one has their own dedicated line. This is the first function, so it goes into the first function of that bit. Second function goes under, third function goes under, and essentially you get these cool triangles. So, I still have to add the compare lines, which I haven't done yet. But yeah. So this is the ALU, fully functional. It's not the fastest thing in the world, and we can actually test out how fast it really is just by seeing how slow the 8th bit, or the very furthest one, takes to calculate. So, if I flick this, then fly over, it's still, there it is. It's just calculated. So as you can see, it's fairly quick, but in the terms of computing, it's not great. It's not terrible, but it's not great. So, yeah. In case you were wondering, each of these, let's use the second bit for example. So let's say we're ORing the number 2 and 2. If we follow these two lines all the way through the adder, well, ALU technically, essentially you end up here, where it splits off. So what's actually happening here? Essentially, this is just a really long line, which is completely isolated. And on each of these little X parts is a gate. So for example, this is an OR gate, goes down there to its result. This is the NOR gate to its result. I think this is AND and NAND. Essentially every single gate is functional all at the same time. Or for each bit individually. Of course I've got 3 left over, hence the 3 obsidian there. I haven't actually got gates for these. Don't think I'll need them, but yeah, better to have them than to need them and not have them. So essentially it calculates everything all at once, which is why it might generate a little bit of lag. But its output for that bit is only dependent on whatever line is active. In this case, the OR function is active, so its output is put to here. If the NAND was active, for example, its output would be along this line. In this case turned off, but yeah, it doesn't really make a difference. So that's essentially the ALU. As you can see in the distance, I've tried copying a few things. And yeah. So this has been a big project. It's taken a while, and I hope you enjoyed watching this. If you want, I'll probably put the download world below. But one thing to keep in mind is that this thing is so large that if it's outside of render distance, sometimes the last couple of bits won't actually calculate, because redstone has to be within the render chunks, or within render distance, for it to actually calculate or do anything. So, that's the ALU. It's taken me forever, but yeah. If you want a tour around this world, I could give it in a different video. So, well, that's me. I will catch you later.